It's my pleasure to introduce Vishal Misra. He's an associate professor at Columbia University, and he's going to talk to us about his work on network neutrality. He's been doing a lot of work in computer networking and performance modeling, and also he has founded the startup Infinio a few years ago in the storage space, and also early was one of the first live microblogging sites, Cricinfo, that he created. That's still one of the most popular sports sites today. And he's going to talk to us a bit today about economic analysis of net neutrality.
Thanks, Jen. Thanks a lot for inviting me here. It's a great pleasure to be here talking about this because a lot of the stuff that I'll be talking about uses Shapley values, and Shapley did most of his work here. So let's start with the talk. I call it Network Neutrality Debate and Engineering Perspective, and we started working on this issue maybe 6 years ago, around 2000, 2007, 8, 2008, and now thanks to John Oliver and President Obama, it's got everyone's attention, and now suddenly people are talking about net neutrality a lot. But a couple of years ago, I discovered this conversation between Hal Varian, Google's chief economist, and Dave Clark, one of the architects of the internet. And I didn't know it was Hal Varian. Last week I was giving a talk and Dave was in the audience. I asked him, so who was this economist? And he said Hal Varian. But whatever I'm going to talk about today is sort of captured in this conversation. And Hal said, the internet is about routing money. Routing packets is a side effect. Then he said, you guys really screwed up the money routing protocols. Dave said, we did not design any money routing protocols. And Hal said, that's what I said. So the whole issue really is, the internet used to be something free, but now so much money is being generated on it and because of it, and that is really the issue that we're facing. So if you take away anything from my talk, maybe the first slide which I stole from Dave, that should be it. But the rest of the talk is, I'll give some background on how we got started, how we started looking at it, and then how it led to cooperative games and Shapley values and application of Shapley values to peering. I'll talk something about some work we did on paid prioritization, which is under sort of heavy debate right now. Should we have fast lanes or not? And then I'll talk about whether having fast lanes is a good idea or not. Now, all this work, I say here it's joint work with Richard Ma, Da-Meng Chu, John Lowy, and Dan Rubenstein. Now, you should use joint in the loosest possible sense. This work was primarily driven by Richard Ma, who was a PhD student of Dan Rubenstein, and he was really the person who came up with this way of looking at things. So it's, I think all credit for this work should go to Richard Ma. He's now a faculty in Singapore. So the way we started looking at it, we were looking at peer-to-peer protocols. BitTorrent was what we were studying, and everybody in the networking community was obsessed with BitTorrent. We were looking at performance of BitTorrent and how and what are the key insights, how do you model it. And then we noticed something else happening around BitTorrent. First ISPs were unhappy with BitTorrent, and they started dropping BitTorrent traffic based on port numbers. Then the community started using dynamic port selection. Then the ISP started doing deep packet inspection and start to look for BitTorrent protocol fields inside the packet. Well, then people started disguising it by encryption. The ISPs started doing behavioral analysis. Just based on timing, the size of the packet, they could figure out it's BitTorrent. And the first real public outcry over this one, people discovered that Comcast was throttling BitTorrent traffic. And we are looking at this whole cat and mouse game going on, and we thought, the problem really isn't engineering, but the problem was rooted in economics. So how should we think about the problem? Maybe, these engineering solutions, this is not solving the problem. You'll keep coming up with some technique, ISPs will try to, thwart that technique. So what really is driving this? And then we said, okay, what were the economists saying about the internet? So we found a bunch of papers, and all of them said, the internet is a two-sided market. One side you have two consumers on the other side, and then in the middle there's the ISP, and that's how you should think about it, and that's how you should analyze. When you think about the internet, it's actually a lot more complex. between users and content providers, there are hundreds of ISPs. So just having this simple two-sided market formalism really doesn't work in trying to understand the problem. So we said, okay, let's try to model this a bit more carefully than had been done so far. So that led us to trying to think how do these ISPs work, and the internet is operated by these thousands of these ISPs. ISP is an autonomous business entity. It provides internet services. The common objective of all ISPs is to make profit. Okay, everybody is trying to maximize their profit. Now, if you think about the ISPs, this again is a taxonomy developed by Dave Clark. You have three kinds of ISPs. Okay. The first kind is an eyeball ISP. It's it provides internet access to residential users or people at the university, consumers. So this is the eyeball ISP. Time Warner, Comcast, examples. Second, you have what are called content ISPs. So these ISPs provide content providers with internet access, and I'm including CDNs as a class of content ISPs. And even companies like Netflix, they have their own CDN now. You can say that they're a content ISP. The line is sort of thin there. And then you have transit ISPs, which provide global connectivity. They connect these transit the eyeball ISPs to the content ISP. They connect ISPs between different continents, different countries. They are the ones that are sort of providing the global core connectivity on the internet. So you have all these kinds of entities that make up the internet. So how should you think about it? So we said, okay, the lens that we should use is something called cooperative games. This was, foundational work on it was done by Shapley right here. So what are cooperative games? So cooperative games are where a bunch of players get together and generate some value. And you have players, the value they generate, and then you also have coalitions, where you could look at a subset of the players and you can talk about the value that that subset generates. So you can have different coalitions and different values that subset generates. And cooperative game theory is all about coalition formation given value allocation. So suppose a bunch of players get together, they generate some value. How is that value divided amongst the players? That's the whole idea about cooperative game theory, and any solution of a cooperative game is basically the value allocation. If they generate this value, how does it get divided amongst the players? And some properties of interest in a solution is stability, where people do not want to deviate from the solution, and then fairness. Is the allocation somehow reflective of the contribution that a player brings to this coalition? Now, a special kind of cooperative game is a convex game. The mathematical definition of convexity is given in terms of this equation for all coalitions A and B. Literally the translation of this equation is that the whole is greater than the sum of the parts. So it also says the marginal contribution of a player increases with the size of the coalition it joins. Now, why is it relevant? It's a very natural model for networks. People talk about the network effect, and there are all these laws. Metcalfe's law, which says the value of a network is n square. Or Lisko had a law, value of a network is n log n, where n is the number of nodes or the size of the network. Now, regardless of which particular law applies, both of them are convex functions, and you can define convexity fairly safely for a network. So what is this property of convex games that we are interested in? So where convex games comes in is, all games will have some solutions. There are a bunch of solutions which are unstable, in which some players actually have an incentive to leave the game. Then there is a set of solutions which are stable solutions. The set of these stable solutions is called the core of this game. So here, nobody has an incentive to leave the game. They are better off being part of the core than not being part of the core. Whereas if you have an unstable solution, some players have an incentive to not be part of the game. They are better off leaving it. Then the Shapley value lies in the center of gravity of this core. So you can think of it as the most stable or most fair of the solutions, where nobody really has any incentive to leave. That's supposed to be the ideal solution for a convex game using the cooperative game theory.
And there's actually one such solution as opposed to kind of a plane.
So
Many kind of traditional game theory has a set of
So this is the whole set of.
Yep.
The Shapley value is one solution. It's a unique value, and it's in the middle. So it's a point in that whole set of things.
Does it always exist?
Mathematically, it always exists. Sometimes it doesn't make sense. And for convex games, it always exists, and it's always in the center of. For non-convex game, you may not even have a core. Forget the Shapley value. So, but we're saying that for networks, convex games makes sense. Okay. So now I'll explain the stability of the Shapley value a little bit more and the core using this simple example, where you have two players. The value that player 1 generates, let's say, is A individually. The value that player 2 generates individually is B. When they get together, form a coalition, the value that they generate is C. So if you look at this figure and you look at the allocation of player 1 as the x-axis and the allocation for player 2 as the y-axis, this line, the red line, defines the core. If you have any allocation within the core, then x is going to be greater than A, y is going to be greater than B. If you have a solution which is somewhere here, then x is going to get more than A, and more than A definitely, but y, the second player, is going to get less than B. So if you have a solution here, B has an incentive to leave. If you have a solution here, A has an incentive to leave. Within here, both of them are improving their position, so that's why they have no incentive to leave. They'll stay there. So that's a stable solution, and the Shapley value is in the middle there. So this is a simple two-dimensional example. It extends to n dimensions. So what is the Shapley value? Well, Shapley characterized the Shapley value through these axioms. So he proposed these axioms in 1953: efficiency, symmetry, dummy, additivity, and then Meyerson in 77 replaced the two dummy and additivity with this axiom called fairness, and Young in 85 replaced fairness with strong monotonicity. But as long as you satisfy these axioms, then they all lead to the same solution, which is the Shapley value. So as long as you satisfy, let's say, efficiency, symmetry, and fairness, you'll get a solution which is the Shapley value. So let me explain what these axioms are. They make a lot of intuitive sense, and I'll explain it in the context of the Meyerson definition, where you have efficiency, symmetry, and fairness. So what is efficiency? Efficiency is very simple. It simply states that all the value generated goes to the players. Nothing gets lost in this allocation. I mean, no one would quibble with that. Symmetry says that identical players get equal shares. So you have these blue players, they're getting an equal share. You have the red players, they're getting an equal share. And the green player is getting something else. Then there is this axiom of fairness or balanced contribution. So what this means is, now let's say you have a coalition and you have generated this value. Now what happens is, focus on one player at a time. This fairness is defined in a pairwise way. So let's say I'm focusing on this player here. You have a coalition, you have generated value, this player has received a certain share of that value. Now let's say another player joins the coalition. Because of the entry of this player, the value of that coalition has increased. And when the value of that coalition increases, the blue player got, some amount more. What the balance contribution axiom says is that the amount of increase for blue when green joined should be the same as the amount of decrease for green when blue leaves. So when blue leaves, when green joined, blue got 2 more. When blue leaves, green should get 2 less. That is sort of the idea of balance contribution. What I do for you, you do for me. So that's
Quick question. Are these dollar signs supposed to represent the utility or actually how much they get paid?
how much they get paid. Okay, so now that we have the idea of what these axioms are, let's try to analyze profit sharing amongst ISPs using these axioms. So we'll start with a baseline case where you have one content ISP, one eyeball ISP, and together they are generating some revenue or profit V. Now one thing that sort of plays into it is the way things are charged on the content side is very different from the way things are charged on the eyeball side. On the eyeball side, it's almost invariably people pay a flat rate. You have these monthly contracts, and so far all the Comcast is trying to change that. So far nobody pays per byte. On the eyeball side, on the content side though, you pay by volume. It depends on the number of bytes that you send into the network that you get charged. But regardless, let's say whatever way you generate revenue, you generate a profit V, then using the fairness axiom, the total profit for each should be half, axiomatically. This is what Shapley value says. Now let's say you have 2 symmetric eyeball ISPs and 1 content ISP. What should be the share? Quarter, and half. That seems sort of fair. Let's see if that is the right solution. So we start with symmetry. There are 2 eyeball ISPs, they are symmetric. We assume that the user is free to move between any of them. They are identical, so the share that they should get is the same. We use efficiency, that all the profit goes to the players. Then we use balance contribution. So same mutual contribution for any pair of ISPs. So if you look at the share that the content ISP gets now versus what it was getting earlier, it was getting half fee, right? Before there was only 1, it was getting half, versus what this new eyeball ISP gets now, and what it was getting earlier. It was not part of the game; it was getting 0. You use these 3 equations, and you solve it. The unique Shapley value actually is even better than that for the content side.
So how are we meant to think about the user here? Is the user connected to both?
It could go to either one.
The user has a choice.
The user has a choice.
Accounts with both.
Yeah, and that is the real problem. Do we have choice or not? So here I assume that the user has a choice. The user can choose Verizon, can choose Comcast, whoever. So this is the sort of fair allocation. Now the presence of one competitor on the other side increases the leverage of the content side much more than what we thought it would. Half and 1/4. 1/4 was a reasonable guess. But actually the fair solution says it should be 2/3, 1/6, 1/6. And you can get a general formula for n symmetric eyeballs where the share of each of those symmetric eyeball ISPs becomes 1/n times n plus 1, and the content is n over n plus 1. So the presence of each additional competitor on the other side increases the leverage of the eyeball ISP significantly.
One thing I found confusing is this. You mentioned before, or maybe I'm just trying to make the situation more complex. You mentioned in the content ISP being both Akamai and Netflix.
Yeah.
Those seem like very different parties in that, for example, a lot of the cost here a lot of the equations seem to basically be based on choice. How many parties can the user go to, or if you're, CBS, how many different CDNs you could choose.
Right.
Is affecting the market there.
Yeah.
But when you're actually talking about YouTube or Netflix, there's actually not choice in that it's a user don't actually, there's not really another party, or the same party as the user on that side and the content ISP.
So are you saying that what if
This distinguishes between the content ISP and the effectively user on the left side of the screen,
yeah.
right? And with a traditional CDN, those are distinct parties. In many cases, and increasingly, they're the same party.
Yeah, and I'll explain
Okay.
why it's starting to make sense, why that's
Okay.
happening.
Okay.
Yeah,
Okay.
but that's a very good point, and that sort of
This is going to explain why that erodes
yeah,
the market.
yeah. So here, the results and implications of the axiomatic solution. Yeah.
Oh, sorry, I was wondering if you could maybe say a few comforting words about the predictive power or empirical validation of this axiomatic framework in
Yeah.
other markets. Because these are very interesting axioms and they're making cool predictions, not necessarily immediately intuitive. So it'd be, I'd be curious to see to what extent they've been validated in the real markets.
You mean the whole theory of cooperative games, or?
This set of three axioms in particular.
So I mean, the cooperative game theory is based on these axioms, and it has been well studied, well used. It's used in all sorts of things like sharing of airport gates by airlines, Shapley-Early solution. In fact, when the channel tunnel between UK and France was built, France suggested that the revenue should be shared amongst the EU nations and UK using the Shapley value. So Shapley values, as a concept it's and what we did was we made some predictions back in 2008, and I'll tell you what the predictions have turned out to be now. Yeah.
I'm a little confused also, just following up on this. So there's a core of stable solutions.
Yes.
And any of these we might see in the real world, I guess, if people
Sure.
act on their incentives.
Yeah.
So why do we care about the Shapley value?
Shapley
Why do we
value
care
is
about both
so I'm not
variables?
saying that this is a prescriptive solution. Your
Right.
solution should be it's a way to think about the problem. And Shapley value is the most stable solution. So even if you have some noise and people are not giving right information, if you're trying to get to the Shapley value, you're likely to be stable. So this is more about trying to think of the problem than really a prescriptive solution that if you have three ISPs, this is the way you should share revenue. It's what defines a stable scenario versus an unstable scenario.
What about the cost for the
So what I say here is it's the profit. So that could be the revenue minus
sometimes the
cost.
profit is
Yeah.
proportional to the cost.
Well, revenue minus cost, yeah.
Sorry, so those equations are not the revenue; they're actually you
The
expect
profit.
profits.
Profit, yeah. So it could be used for profits and costs as well. So the whole theory also works if you get together and you're incurring a cost in building something, then the same axiom sort of apply. How much should an individual pay?
I have a question.
Yeah.
So, moving beyond cooperative game theory, so Shapley value is maybe a good choice for thinking about it in that lens, but just like more basic economic theory, if you have C1, B1, and then you add a B2, B1 and B2 are basically going to Bertrand compete
Yeah.
away the surplus, and they're going to end up with nothing. So,
Wow.
why is cooperative game
Well,
theory?
they won't end up with nothing, right?
They won't end up with nothing, but they're going to end up with, say, a lot less than perhaps the Shapley value indicates. So why is Shapley value, cooperative game theory? a
Again,
better
I
approach
think
than
it's
sort of
it's a
more
good tool to
orthodox
think
theory?
about it, to think about the solution and what it tells you, where the
You know, we have a very precise prediction from sort of this orthodox economic theory.
well, we couldn't find anything, so we used this and we came up with these predictions, and
So you're
it
not
sort
going
of
to take it as the data in any way.
yeah,
then?
we had data.
Oh, you do have data.
Yeah, we had a lot of data. Yeah.
How should we think about these tools with respect to other tools in game theory like Nash equilibrium?
So, there's a whole religious war between non-cooperative and cooperative game theory, and people say every cooperative game theory should be. I'm not going to get into that debate. Religious war. I have just used. I'm not a game theorist. We just started using this framework to try and understand, and we think that we arrive at some interesting conclusions. So let me continue, and then at the end of the talk we can revisit those. In fact, the second part of the talk we did Nash equilibria. Okay, so now if you sort of generalize this to now you have multiple content provider ISPs and multiple eyeball ISPs, what is the share? We can derive the share to be this. And what it really says is each ISP's profit share is inversely proportional to the number of ISPs of the same type that it has. So it's competing, which sort of is the intuition, if you're competing then you get a lot less. And it's proportional to the number of ISPs of the other type. So the more you have competition on the other side, the better off you are. The more you have competition on your own side, the less. So again, it's not sort of disputing the intuition, it's just giving some numbers around it. Try and think, what are the implications. Again, so it's now you introduce transit ISPs into it and you get some really ugly looking equations, but the behavior of the equations is the same. The intuition that you derive from these equations is essentially the same, nothing changes. You want competition, more competition of the other kind, and then you have all these sort of shares. So, when we were doing this work 2007, 2008, the kind of bilateral settlements that were very common amongst ISPs were either you had a customer provider relationship where an ISP bought bandwidth from an upstream ISP, or consumers or content providers bought bandwidth from ISPs, and there was this customer provider relationship, or you have $0 pairings, where settlement pairings, the transit ISPs, they paired with each other, they exchanged traffic, and no payment was done. So, given that, and let's say you have I'm representing the topology of the internet by using this cartoon, right? You have content ISPs on one side, eyeball ISPs on one side, transit ISPs in the middle, and you have some content side revenue, you have some eyeball side revenue. And then content ISPs pay the transit ISPs to get bandwidth, eyeball ISPs pay transit ISPs to get the bandwidth. Now, there should also be a flow on the other side, but since there are these flows coming in, these kind of bilateral payments could achieve a solution which was stable. Just by doing these bilateral payments, if the content revenue was roughly similar to the eyeball side revenue, you could achieve a solution which was the Shapley value solution. So that's the way to think about it, that okay, if you just did this bilateral and you did not have this whole oracle sitting there computing Shapley values for you and saying okay, you get this, you get this, you get that. If you just followed the natural order of things, what was happening, your bandwidth was being bought and sold, then you could get a stable solution. Now what happened in the late 90s was two things. One thing was, the internet was early on, it was a very symmetric network. You had light, email and web traffic flowing between users. So the volume of traffic on both sides was about the same, and there was really no commerce being generated on the internet. What started happening in the late 90s was you started getting well-defined content providers and well-defined eyeballs. So the volume of traffic shifted dramatically. It was going from the content side to the eyeball side. Plus, there was this whole economy being generated because of the internet, on the internet, but nobody was paying, money to the content ISPs or eyeball ISPs for this economy. They were just paying for bandwidth. Right? People were just trading bandwidth. Now, a packet of Google is much more valuable than a packet of, let's say, just somebody's blog. Now, leave aside volume pricing, volume discounts, Google is paying the same amount for that packet as somebody who's running a blog on the internet. So these ISPs are sort of getting cut out from that action because of this whole other economy that was built on the internet. ISPs were still trading bandwidth, but what the content providers were really getting was this revenue which was outside.
I mean, there's a whole other narrative about that says that other people were creating value that was unrelated to the ISPs, and why should the ISPs get a cut of that?
So what the argument here is that without the internet, the internet is like a veto player. You take the internet out, and this whole economy collapses. So what we saw that if there was big asymmetry here in the content side revenue and the eyeball side revenue, and now you can include the money that is being generated because of the internet as part of, let's say, the content side revenue. You move into the content, because what's happened is content ISPs became a proxy for the content providers. If there's asymmetry here, then what we found out was there was no way you could achieve a stable solution through these bilateral payment. If you're just trading bandwidth between these guys and these guys were selling bandwidth to the other ISPs, you could never achieve a stable solution whenever there's asymmetry. On one side, it could be, eyeball side revenue could be much greater than content side, or the other way. So what we found that, there was no stable solution.
Question.
Yeah.
You mentioned revenue here, but if we were talking about profits, does it
I
matter?
use that interchangeably. Everything works, it just becomes, the formulas become a little bit more complex. You need to extract that out, but I'm using it interchangeably, I'm sorry. But yeah, think of it in terms of profit.
The only reason I ask is it seems like the fixed cost for eyeball ISPs is so much higher.
Yeah. So that I'll come to that.
So the assumption here is that the content people benefit more from the existence of the internet than the users do?
They are making money, or the users are paying, right?
Sure, but users are getting utility.
Yeah, they're getting utility, but they're paying for it, and the money is sort of, if you look at the this figure, the money is going around the internet. It's not being traded in terms of bandwidth. You're making direct payments to Netflix or to Amazon or to Google.
Sure, but if you're doing economics, you care about utility, right? And so the user, if the users
Users
are
getting utility, no question. It's not that everybody is losing out on utility.
So
It's really who's getting the money, who wants the money. That's really the.
I don't think it's a given that most of the utility is being extracted on the content side from the existence of the internet, right? You can make a pretty good argument that users get most of the benefit of the internet.
Well, along those same lines, in the old days, when you had a dial-up modem, you couldn't watch a Netflix video.
Sure.
You didn't have the bandwidth.
Yeah.
But you didn't pay that much in relative
Well,
terms. So now the user, in order to go, hey, I want to watch Netflix, I will pay my eyeball ISP more money to get more bandwidth,
Yeah.
and then I can watch Netflix.
So there's market pressure on that side that the users don't want to pay all that much. But Comcast wants money from Netflix. The ISPs want money from Netflix. So what we sort of said that because of the situation that we observed, you could not have a stable solution. We said what you really need here is paid peering, where these eyeball side ISPs, if there is the revenue there is lower than the content side, these transit ISPs should not be selling bandwidth to the eyeball ISPs. It's more a case that from the content side you're trying to sort of buy eyeballs. So you should have more of these paid peering arrangements. You don't have settlement free peering, but you're paying for bandwidth. So that's what our prediction was, and Netflix now has a paid peering arrangement with Comcast, with Verizon, with AT&T, with what's the fourth one? The Time Warner, right? Yeah, they're cutting out transit. They're dealing directly, and this is the percentage change in Netflix download speeds since 2013 by ISP. This is the point at which Netflix entered a paid peering arrangement with Comcast, right? And all the other three, Netflix has now entered a paid peering arrangement with them as well. So,
I've never read it. Is there evidence that Netflix was slowing down the traffic, or did they just under provision the?
no, so
peering
one of the content ISPs that Netflix was using was Level 3. Level 3 has this huge blog post. I don't know if you have seen
I read
views
it,
of
I
an internet middleman, and they said that all of their ports on these exchange points were operating at 30%, 40% capacity, except for they did not name the ISPs, except for some ISPs which had a monopoly in their region. Their ports were consistently running at 95%. For over a year, Level 3 kept requesting them, let's just upgrade the ports. It cost like $30,000. It's noise. They refused to do that. Right? So all of them, so Netflix has Level 3 has detailed data on that everything else is running fine. These ports are consistently blocked. They're requesting, just add more ports. It never happened. What did happen was paid peering arrangement. And we sort of said, we were predicting that this is going to happen because you need some flow of money to get to a stable solution. More money needs to come in this way.
What do you mean when you say more money needs to come in?
So to achieve a Shapley value stable solution, earlier when things were symmetric, you could just have these bandwidth transactions here, and the solution that you achieved was stable. But if there is heavy asymmetry here, then to get a stable solution,
Asymmetry is
in revenue, in the revenue.
utility.
No, not revenue. I'm just talking about money, directly money. The amount of
How do the eyeball ISPs know that somebody's paying Netflix or paying? How do they know that money exists? I mean,
Google's.
no, but I mean, how much is it, and how
It's all public knowledge. Everybody knows what Google is making every quarter, right? What Netflix is making every quarter.
So
How much?
eyeball ISPs are just like, because those guys are making money, I
We
want
want,
something.
we want,
But
and
here-
because they have the monopoly,
and I can turn
because
off
they have the
money.
monopoly, they can do that, right?
I see.
Here,
So-
Vishal, here's
Yeah.
the question I was asking about revenue versus profit. So,
Yeah.
Netflix or Comcast, probably charge a household for internet alone is $500 to $1,000 per year
Yeah.
per household. Google's revenue is on the order of 50 billion.
Something like that.
They have 1 billion users. That's about $50 a month. $50 a year per user.
And that's one content provider.
Right, but wouldn't this actually suggest that there's way more? I mean, the way you said there's so many content providers, and in fact, it seems like
Think of it in terms of this formula.
it sounds like the ISPs are getting overpaid.
No. If you think about this formula, you also have to factor in how much content is out there. Right? If Google is not working, you'll go to Bing or you go to some places. Netflix is not working, you'll go to Hulu, you go to Amazon. All of them are like competing for the need of the user to get internet. Right? But if my Netflix is not working, I won't cancel my internet service because I have all these other things.
No, I understand.
So the issue really is the asymmetry between the amount of content that's available, that the user that get utility from that content, choices you have. So that's the leverage that the eyeball ISPs have, that the number of choices for the users is very, very small.
So this is essentially an argument that Comcast has a lot of market power, perhaps monopoly power, and naturally they end up with all the money.
Yeah, that's basically the
Why are
argument.
they losing money and Google's not?
I think
So
Excuse me. It's also that content is not just what goes through the internet; it's also the products sold through the internet.
yeah.
The
So I'm saying that
electronic commerce. Yeah.
all of that is included in this extra money that is being generated. So this whole economy is running because of the internet, and they say, well, we are just selling bits. We want, and so what the theory really says that they're not unfair in asking that.
Wait a sec.
Yeah.
I think you're conflating two things. One is a prediction
Yeah.
about what the solution to the equations is
Yeah.
under competition, which
Yeah.
says that the person who has monopoly power gets all the money. And another is the should.
Should,
That's
yeah.
a
So I'm
desirable
saying that the
outcome.
theory says that what's happening
Theory says it will happen.
it is happening, right?
Yes, okay.
It is happening.
okay.
It is happening because what we said that the current situation is unstable. And in 2007 or 2008, there was a fight between Cogent and Level 3, and they just cut off the connection. That's like, they take my ball and go home. I don't want to play. 15% of the internet was cut off because of that.
This is where right. So should is a
Yeah. I'm saying the theory
is a
says.
kind of slippery word here. Will is
So when you
what we're
presented the
talking
original
about.
model, you presented it as consumers having choice of ISPs on the eyeball side.
No. even then the situation was clear that consumers don't have choice on the eyeball side.
But so when you presented the original model, there was this little dashed line from a consumer going to one of many potential ISPs. Does anything change when you don't have that choice?
Yeah, if you don't have that choice, then this happens, right? That's what I'm saying. This happens. People have market power, and they'll flex that market power to extract something out of the content side. So when I'm showing the arrow, I'm being an academic. Suppose you had multiple choices, you have only one content provider. For the sake of argument, let's build a theory. What the reality is this. Yeah.
So why was Cox speeding up? Because presumably they have some monopoly or duopoly power where they
Maybe they were competing. Right?
Do we know that? We must know
Yeah,
if they were
yeah.
in more competitive markets.
So
than the others.
these were the four sort of that Netflix ended up signing paid pairing arrangements with. They did not need to sign with Google Fiber or Cablevision or Cox. So maybe they are competing with other ISPs there, and they are doing what's good for the consumer. You want good Netflix? Come to us.
But that's knowable, right? I mean,
Yeah.
have you looked at data on?
Yeah. So what the level 3 data said that the only places where they faced this issue was where the monopoly ISP.
But do we know that Cox is operating in more competitive markets than
I-
Verizon or?
I'm pretty sure we can
Comcast.
get that data. Yeah.
But you haven't looked at it yet, so that's.
We did look at it, and we said that these were the four that were really monopolies. In fact, when the Time Warner Comcast merger plan was announced, the CEO of Comcast said, this is not going to actually reduce competition because we don't compete with Time Warner. That's not an explanation, that's a question. Why are you not competing? Right. So it's like they have cordoned off the markets, and then each one can flex. So another related thing that I should say is that in the UK, they have zero net neutrality rules, but they've paid a lot of attention to competition and to transparency and performance. And even in the UK, some providers were doing this traffic management, where in the evenings they would throttle BitTorrent and all. And then one ISP said, we're not going to do that. That you can say is like Cox. It started getting all the business. Now none of the ISPs do it. So the point really here is, people talk about network neutrality and Netflix fight with the ISPs and get better service and all. It's all a fight about money and competition. Nobody is really able to define what network neutrality is precisely, and there are so many tricks that we can play, which falls under network neutrality, but really screws content providers. From MPLS to these paid pairing versus non-paid pairing, AQM. There's so many of these seemingly innocuous things that you could do, which will have the same impact. The way to solve this problem really is to focus on competition. And a big issue really is the investment in the last mile. So transit prices have fallen by 2-3 orders of magnitude in the last 15 years. Content ISPs are getting paid 1,000th of what they were getting paid earlier. One of the reasons is it's much simpler and much easier to throw a fiber at the Google data center than to dig the last mile for every household.
I think the same with the submarine prices has also not dropped that much.
Yeah.
They've been fairly stable over the last 5 or 10 years.
Sure. So it's
to lay submarine cable.
Yeah. So it's a last mile investment. So if instead of focusing on network neutrality, people focus on things like local loop unbundling or making really the last mile as a common infrastructure that anybody can come and provide you services with. That's a much better way to go than network neutrality.
You could also rules of the game. You could introduce legislation or something.
Yeah, you could. We have an excellent track record in terms of registration.
I'm not saying it's a good solution or not, but it's a way.
Yeah, but
Europe has this, or Spain has this. There's certain last mile. They're like, for example, I think in Spain, like utilities has this in the U.S. right? The party that generates and distributes are separate.
They're separate.
For power, yeah.
There was legislation about this in the 90s, right?
Yeah, so that was the telephone, not for
No,
that.
but the legislation failed for internet, right?
Yeah, and which I think is an issue. So a lot of this network neutrality debate is about should people have fast lanes or not? Should fast lanes exist? So we decided to let's look at the issue of should we have fast lanes? Network neutrality is good, or paid prioritization, which is basically fast lanes. Does it make sense? What can happen? Again, we listen, and what we saw, for these papers which says treat the internet as an MM1 queue. I had no idea what the M was. Are you talking about packets? Are you talking about flows? Are you talking about objects? It made no sense what what it meant, and let's say the queue size is the quality of service. So again, we said, okay, let's try and build a better model of what really happens on the internet, and then come back to analyze it. Sort of what we did with using, looking at multiple ISPs and not a two-sided game. So we developed this three-party model, where now we focus on the last mile, the access ISP. And let's say the access ISP has some capacity mu, let's say to the cable head end, or the last mile, just before the last mile. M is the number of users of that ISP. N is the set of all content providers, and lambda I is the throughput rate of each content provider. I'll explain why all this makes sort of sense. So you have these users, M, you have all these content providers, and each content provider is sending traffic through this last mile pipe at some rate, lambda I. Now, on the user side, you can't just say every traffic is equal. You have different aspects of a traffic. So one, you have the unconstrained throughput from a certain content provider. So let's say for Netflix, the unconstrained throughput, if there was no congestion, would be something like 5 megabits per second. Google search traffic, 100 kilobits per second. We did some rough analysis of what a search page looks like, how much time does it take to come back with a search result. So different content providers have different requirements on the unconstrained throughput. Then different content providers have different levels of popularity. Everybody uses Google, not everybody uses Azure or Bing or Netflix. Then there is also a demand function of the content, which we thought was really important to model. This is the percentage of users that are still active when the throughput that you get is less than the unconstrained throughput. And different content providers behave very differently in terms of this demand function. Yeah.
The demand function at theta I, is it just content provider specific, or is it a vector of all the thetas for all the content providers?
Content provider specific. So this is so here's an example of different demand functions for different kinds of content. So here you have a demand function for a Netflix-like content, streaming content, where as soon as your achievable throughput falls, the number of users leave rapidly. Right? Some users will stay, some users will watch it at the lower bit rate, but most of it will go away. Then you have the Google kind, where you have a lot more elasticity. Even if your search results are twice as slow, thrice as slow, you'll still go to Google. And then you can have things in the middle. So it's sort of that's the demand elasticity.
So I guess then my question is, since it only depends on the own content provider's throughput, doesn't directly depend on another content provider's throughput, this kind of story you were saying earlier about how easy it is for users to substitute between different types of content, and how that disempowers the content providers.
Yeah.
That's not going to be present in this model.
That sort of plays into this model, because now we have a more detailed model where we have the popularity of a content provider, the amount of throughput that content provider demands, and how many users remain after that throughput is not achieved. So
you don't have something like with Netflix and Hulu, and if Netflix gets throttled, then people will substitute to Hulu.
if Hulu is getting
Right, but that's only through a general equilibrium mechanism, right? So if Hulu gets more allocation,
or Hulu could go into the fast lane.
Okay.
I'll come to that.
All right.
Yeah. So then we had a system side rate allocation where the throughput was upper bounded, the link was work conserving, there was some monotonicity property that if you increase the link capacity, then the throughput achieved is strictly increasing. So all sort of very reasonable assumptions, and under that we said that there's a uniqueness of the rate equilibrium, where if you have all these content providers with their popularity, with their demand function, and then you have the users, of a constraint pipe, then you will achieve some sort of a rate equilibrium, where each content provider would get a certain amount of throughput and it will serve a certain number of users. So then what we did was, okay, let's take this model and let's look at two scenarios. One scenario is where you have a class where content providers pay per volume of traffic to get into the premium class, and then there's an ordinary class. So content providers can choose. The ISP can announce certain charge per unit traffic. It can allocate a fraction of its capacity for this premium part, and the rest of it is the ordinary class. So you end up with two different kinds of rate equilibria, the amount that's going in the premium part and the amount that's going in the ordinary part. So the payoff of the ISP is the total volume of traffic that goes through the paid part. That's the extra money that it can generate. So we did a monopolistic analysis where you have a two-stage game, where in first stage an ISP announces the fraction. Well, it doesn't really announce the fraction, it chooses a fraction that will reserve for the paid part and the price that will charge for the paid part. And then in the second stage, all the content providers simultaneously decide whether they want to be in the ordinary class or they want to pay and get into the premium class. So, Hulu can be paying and be part of the paid class, whereas Netflix is facing congestion in the other part. And the outcome are the two subsystems. The ISP surplus is the revenue that it's generating. The consumer surplus is, the consumers have different utility per unit traffic of different content. So it's the sum of the content times the throughput it's getting. And the content provider, if it's in the ordinary class, it's the per unit traffic profit of content provider. So but it could be explicit or it could be based on some averages that per search Google generates this much revenue. You could come up with numbers for that. Or if it's in the premium class, is the profit that it's generating minus the cost it has to pay to the ISP. So under this scenario, you could have different kinds of content. The profitability of a content provider increases on the y-axis. The utility to the user increases on the x-axis. Not really very important what precisely they are, but roughly to give you a guideline. And what we did was, we did this monopolistic analysis and we computed the Nash equilibria, and we saw that the monopoly ISP has incentive to allocate all capacity to the premium service class. So what you really can have is a damaged goods scenario, where the ordinary class has such bad performance that everybody is paying to get into the fast lane.
So if everything's the fast lane, is there not really a fast lane anymore? Is it just a matter of just keep charging more and more until you get
to that equilibrium?
So if a lot of internet connections are provided by companies that are also selling paid TV services.
That's a big
well.
problem. I'll come to that.
Are you going to get to that?
Yeah. That is a problem. 5 minutes, okay. So so the implication is that ISP should not be allowed to use non-work conserving policies. Right? Kappa cannot be too large, the fraction that is allocated to the paid prioritization, and how much should we allow the ISPs to charge? And then ultimately, there's no fast lane and everything is just priced higher. Then we did an oligopolistic analysis, a two-stage game model, where you had competition, and the users are free to now move between ISPs to maximize their utility. And what we also did was we did a duopolistic analysis where you had an ISP that was doing paid prioritization, and then you had this public option ISP, which voluntarily did not do any paid prioritization. It said, okay, everything is neutral. And what we saw was that if you had such a scenario, which we called a public option 2 years ago, then we show that if the ISPJ is a public option so that it's not doing any paid prioritization, then the ISP that is doing paid prioritization will work in such a way that to maximize its market share, it's also maximizing the user's utility. So the presence of this competition, just one ISP which is doing network neutrality, no prioritization, gives an incentive for the other ISP to behave in the right way.
Why does actually having no prioritization increase a user's utility?
So because what happens if with prioritization, okay,
For example, I can imagine BitTorrent, where in the BitTorrent examples, their argument was probably valid that a small fraction of users were actually ruining it for everybody else.
True. What's happening here is that you could have ISPs of or content providers of this kind who have a lot of profit and who can afford to pay, but they don't have a lot of utility for the users. And then you have the little guys that don't have a lot of profit, but they provide a lot of utility to the users.
I can imagine that scenario, but is that actual the real world?
We use some models, different kind of distributions. This is a possibility that could be there.
Sure.
But we said under all sort of distributions of these kinds of content providers, one thing that became clear was the presence of this public option ISP resulted in a scenario. Yeah.
So the assumption is that the non-public option ISP is trying to maximize its market share.
Its market share.
As opposed to trying to maximize its revenue.
Profit. Yeah, and which again sort of becomes the same thing. But to do that, it has
Is
to.
it in this model, is it the same thing?
Approximately the same thing. Yeah. But in the other model, it doesn't care about the user because the users are sort of trapped. You'll just try to increase it. The presence of this other public option ISP forces the ISP to behave in the consumer's interest, which is what is sort of happening in the UK. Yeah.
So what are your assumptions about the capacity of the two systems?
So what
because there
we
could be
assumed was
some-
that the public option ISP somehow can get lease lines like local loop unbundling. So we proposed a bunch of different avenues to achieve this. One way is municipal broadband, where the municipality lays out its broadband and it leases it out to anyone who wants to be an ISP. So yeah, it's important how much capacity that, right? If the competitor, the free public option ISP has no capacity, then it won't make a difference. It needs access to the last mile, which is again the same point of the first part of the talk. So if you have competition though, we said that no rules is better than having network neutrality, and public option is not really needed if you have competition. But the problem is we don't have competition. So the regulatory preference is that if you have monopoly, then doing nothing is bad. Network neutrality is better than doing nothing. The best is have a public option. If you have oligopoly, then don't do anything, the market takes care of things. If you really have competition and people are free to move, they are not bound by these monthly or yearly or 2-yearly contracts. This was a different context, but you could say cable industry, and it's still the same. Now, do I have a couple of minutes or?
Some people are going to probably have to line up one.
Okay. So wireless, there are some differences. One of the differences in wireless is people on both sides pay per unit charge, and then there are these zero-rated apps that have started appearing, which don't count against your bandwidth. That makes things more complicated. And what's happening is, the wired network neutrality debate, they suddenly now want zero-rated apps. They're on the opposite side. So Facebook and Google and everybody wants zero-rated apps, which is very anti-competitive. So there are some significant differences in the wireless scenario. We are working on it. Last mile is less of a problem. Multi-homing is the ideal thing to do, and Apple recently introduced this thing called Apple SIM, which was very easy to change providers. But of course, AT&T stepped in and said, if you join AT&T, then you cannot join any other ISP. But we need things like more competition, multi-homing, ability to choose ISPs, and then you don't have to worry about network neutrality. Well, I'll stop here. Some of the papers that we did, and I'm happy to talk offline to anyone.